So in this particular session, we are going to see about FPGA configuration, like how we are configuring our FPGAs. We have already seen that we can configure our FPGA because it is going to have CLBs. Further, it is going to have LUTs with it, right? Now, who is going to configure, right? So we are going to have something known as bit file. Okay, so this bit file is going to configure our FPGA. Okay, so whatever the Verilog code which we are going to write, or whatever the VHDL code which we are going to write, that is going to be converted into a file which is known as bit file. Okay, so what is a bit file? So a bit file extension is normally .bit or it is .bin, and it's a configuration data file that is going to program our FPGA fabric. Okay, so it is going to define every aspect of our hardware logic, like how what are the LUT contents, and what should be our flip-flop configuration, how many LUTs should be present in inside our FPGA, what should be the routing which should be present between these LUTs or the logic blocks, and what should be the IO standards, like which input output should be connected, which pin should be connected, what should be the clocking resources and timing. Everything will be present inside this .bit file. And who is going to generate it? The tool is going to take care of this everything. What is our duty is to write the Verilog code, that is also an optimized Verilog code, such that we are utilizing our LUTs correctly. Okay, so our duty is to write the Verilog code, and the tool is going to take care of the generating the bit file and loading the bit file and configuring our FPGA, right? So is the bit file is it clear? Any doubts or any queries in the bit file? Please let me know in the chat box. So this bit file, basically, in the case of our SRAM based architecture, the FPGA uses SRAM for storing the configuration data internally. Okay, so this bit file or the bit stream is stored inside your SRAM, which is present inside your FPGA itself. And whatever the bit file, you can store it inside your SRAM. Okay, and this is volatile in nature, as we have already discussed about this SRAMs. These SRAMs are volatile in nature. So if you remove the power connection, all the data or all the configuration data which you have stored inside this SRAM will be erased, and your bit file or whatever the FPGA which you have configured, that will be in a reset condition. Okay, so basically this is reconfigurable. This FPGA is basically reconfigurable and can be reprogrammed unlimited times with different designs. Okay, so this using this bit file and reconfigurability concepts, you can reconfigure your FPGA for n number of times. How many number of times you can, if you want, you can reprogram it that many number of times by generating the bit file and by loading that bit file into the FPGA. I mean into the SRAMs. Okay. Now, so we also have some of the external storage solutions, like because since your FPGA SRAM is volatile and your bit file will be erased if you remove the power supply, right? So bit files can also be stored outside the FPGA chip. So one of the option is SPI flash memory, and another is QSPI flash memory, and also processor memory, or also host PC via JTAG connection. Okay, so there will be something known as JTAG connection. Okay, so using this JTAG, you are going to program your FPGA. Okay, so those and all things we will see when we have the hardware. So, but please try to understand that we have three type of sources which we can use. One is SPA flash, where you can load all the bit file related thing inside this SPA flash memory, and this is non-volatile. Okay, and also you can use this QSPA. Okay, so these two are different technology memories. One is SPA flash memory, and another is quad SPA flash memory. This is faster compared to this SPA. Okay, and you can also store the external processor can also store and manages the bit file deployment, that this case study we will have. Okay, this last two case studies we are going to discuss later. Okay, so this is how you can able to reconfigure your FPGA data or FPGA behavior, and you can store the bit files into the external sources or in the internal sources, which is nothing but my SRAM. Now, let us try to understand what is the process of generating your bit file using Vivado software, right? Let me share my screen again. So for this session is the prerequisites is Vivado tool that is necessary, and another is Verilog language is also necessary, right? Now, let me show you the demo of how you're going to use Vivado tool for generating your bit stream or bit file. Then you can, after installing the Vivado tool, you can also explore that, because since you are going to have anyways recordings, right? You can follow those. Okay. Now, so I've already opened my Vivado tool. So this is my Vivado tool interface, which I'm going to have. If I open this, this is the interface which I'm going to have, right? Now, what I'm going to do is I'm going to just click on the project, create project. Okay. So this window will appear if you click on this, and it is going to ask you to create a new project. Yes, I want to create a new project. So I need to give the project name. Let's say bitfile example is my bitfile example. And after giving your project name, you need to change your project location also. Let me change the project location. Uh, yeah. So I've created my project location and I'm going to click next. And it is asking whether I want to create a RTL project, or whether I want to create a post synthesis report, or whether I want to create a IO planning report, or whether I want to import a already existing project, or whether I want to create an example project. No, I need to create an RTL project. So just click on next. Now, here it is basically asking you the source file which you want to have, right? So, just if you already have the files, you can click on add files, or if you have the directories where the files are present, you can add directories. And if you want to create a file, you can just click on create file. Okay. Now, after pressing on create file, it will ask you the file type. So there are different options like Verilog, Verilog header, system Verilog, VHDL, or memory file. We are going to deal with Verilog, and the file name is, let's say, if I'm going to develop a simple half adder. Okay. So this is my file name which I'm going to have, and don't change the file location. This is file type, file name, and file location, and press OK. That's it. So one file is created. Simultaneously, you can create more number of files by again clicking on create file and thing. Okay. And also you can create the file after creating the project also. No need to worry. Okay. Now, and just click on next. Now, there is one more option which is known as constraints. Okay. And this is optional. But if I'm going to work with an FPGA, where if I want to access the IO pins like push buttons or LEDs or those particular things, I need to provide these constraints. How to provide the constraints and all, we will discuss. Okay. Just for now, I'm going to skip this part. Okay. Now, here comes the board selection. Okay. Now you can either enter the part number over here, or you can go to boards section. Okay, let me go to boards section, and the board which we are having is Zybo Z7. Okay, so I'm going to search for something known as Zinc Zybo Z7. So let me check where it is, or I can simply write down here Zybo. Okay. Now you can see the board part is not present. Okay. So normally what is going to happen is, if you are installing Vivado, some of the boards will not be installed. You need to again go to Digilent. Okay. So I will show you what is Digilent. So you need to go to Digilent boards download. Okay. So from the online digital Digilent board, these particular things you can download. Okay. I will provide you exact GitHub link where you can download the boards. Okay. So that particular FPGA boards, you can download it. Now we are not going to download these particular things. We are going to just enter the part number. That's enough for our project. Okay. Now, how to enter our part number? So I'm working basically with Zybo Z7. So what I'm going to do is, I'm going to go to Google, and if you have Zybo board with you, you can just simply see the part number available. But as we are not having board with us, what are we going to do is, we are going to simply search Zybo Z710 part number. Okay. So we can get the part number as XC7Z. It will be something like XC7Z010CLG400C. This is a part number. Okay. This we are going to enter over here. Okay. So then we are also not able to get this. Now, what to do is simply erase this. Now, here go to category and click on all, and package it is CLG. So the package is CLG 400. So click on CLG 400, CLG 400, right? And temperature leave it, and family go to Zinc 7000 series. Okay. Now you can select your board. So we have over here XC7Z010 CLG 400 minus 1. I'm going to select. Okay. So you can see IO pin count is 400, available IOBs is 100, LUT elements is, yes. Which part exactly? Yeah. Okay. So first we need to check for the part number, right? So the part number is XA7Z010 minus 1 CLG 400C. And if you simply copy paste over here, it might not show exactly where it is present. Let me copy paste over here. It is not going to show you. Okay. Now, what you can do is you can add the filters. What are the filters I'm adding? The package is CLG 400 and the family name is Zinc 7000. Okay. So this two filters I'm adding so that I can see the board over here. It might due to the this is capital letters and this might is small letters. So that's why I think it is not showing. Okay. So you can add these filters and you can find out the board part number over here. Okay. For this particular part number, I'm going to have 17,600 LUT elements. Okay. And 35,000 flip flops I'm going to have. And the block RAMs I'm going to have is 60. Okay. And ultra RAMs I'm not going to have. And DSPs are 80. And BUFGs are 32. And GB transceivers and this and all things. I don't have this in this particular specification, right? So you can see all zeros over here. Okay. And all are this particular zeros and minimum operating voltage, difference operating voltage, maximum operating voltage. These are all the specifications of this part number, right? And you have entered your part number, you have selected your board, and you can just click on next. That's it. Your project will be finished, and this is your project summary. Okay. So, how to create your project, how to select your part number, these are all things. Are they clear? Any doubts or any queries? Please let me know in the chat box so that we can move forward. Okay. Has been created and it is asking for to define the module. You can give the module name over here and click on OK and click on yes. Okay. So the file will be created. Let us wait for the file to be created. Yes, the file has been created. So this is the interface you're going to have when you are going to create a project and open a Vivado. Okay. Whatever the version you're going to take from 2016 to 2025, this is Vivado 2025. From the version 2016 to the version 2025, the interface is same. Okay. Xilinx Vivado interface is same. Okay. Now, what is that we are going to have is on the left hand side, we are going to have something known as Flow Navigator, and in the middle, we are going to have something known as project manager, where we are going to have something known as sources, properties, and TCL console, whatever the messages we are going to get over here. And these are nothing but my messages. And this is nothing but my log reports will be given over here. Reports, design runs. Okay, this and all we will explore later. Okay, don't need to worry about all these particular things, right? And here we are going to have something known as our project summary. So in the project summary, your project name will be given, project location and product family, project part number, top model name. Top model we haven't defined yet, and target language, simulator language, target simulator. Okay. And synthesis reports. Okay. Implementation report, DRC violation, design rule check violation, timing reports, utilization, power, everything will be given over here. And this is nothing but my overview. And if you click on the dashboard, everything will be given in the dashboard. Okay, let me show you after running this particular thing. Okay, yeah. Now if you want to type something, or if you want to write your Verilog code, what you need to do is you just double click on this file which is known as half adder. Okay, so this file will be open. Okay, you can maximize it. I'm just going to declare the inputs and outputs, and I'm going to write down simple code. Okay, yeah, so this is the code which I have written for my half adder. Okay, and if you want to save it, you can click on here or you can click Control plus S. That will be saved. Now, after saving this particular file, you need to make sure that this is in bold letters or this is in top module. Okay, only the file which has been set as top, that is going to be synthesized, and for that only bitstream will be generated. So you need to make sure that this particular file is in top model. How you are going to make sure? It is in bold letters. Okay, now let us say if I'm going to create one more file which is FA full adder, and let me click OK and finish and click yes. So another file has been created. See, so this full adder is written normally without in bold letters. Okay, now the bit file will be generated for this half adder because it is set as top. Now let's say if you want to generate the bit file for this full adder, then you should make this full adder to top. You just click set as top. So the full adder will be set as top and the bit file will be generated for only this file full adder. At a time you can generate bit file for only one particular code, right? Now, so I'm going to make my half adder to top. So right click on it and click on set as top. Okay. So my half adder or my Verilog file which I have written will be set as top. Okay. Now, after that, what I need to do is in the project manager. So these are the steps which I'm going to have. What is create block design? I will show you. Simulation is basically if you have watched my old videos on Verilog. In the Verilog playlist, we have used this particular thing a lot. We have written the test benches and we have ran the simulation. If you haven't watched those particular sessions and if you don't know about this Vivado, you can go and please rewatch that where we have used this Vivado tool for running the simulations. Okay, and linter file and open elaborated design. This elaborated design is basically going to give you the elaborated diagram, logical diagram for this. Let me show you. Open elaborated design and click OK. So it is basically generate. It is going to generate the netlist for the Verilog file which we have written, and it is going to open the logical elaborated design for us. Let us see what it is generating. Okay. Meanwhile, please let me know. Is it clear? The steps are they clear? Any doubts or any queries? So this is the elaborated design which was generated by the tool. Okay. Now, after this elaborated design, you might or you might not use this elaborated design. It's up to you. Now, after performing synthesis and implementation, we are going to have something known as generate bitstream. If you click on this generate bitstream, synthesis and implementation both will be done at the same sequentially. First, synthesis will be done and implementation will be done. Then bitstream will be generated. Okay, you can click on run synthesis. Next, you can click on run implementation, and next you can click on generate bitstream, or else you can directly click on generate bitstream. Okay, so implementation and synthesis will be done automatically. Just keep everything to defaults and let us wait for the bitstream to be generated. Now, way to check whether the bitstream is getting generated or not is on the right hand side top, there is some loading button, right? So the synthesis design is happening basically, and next implementation will be done, and after that bitstream will be generated. So let us wait for that bitstream to be generated. Process. So we need to have some patience when working this with this Vivado, and that is why if you're like let's say suppose if you're running some particular designs and if you feel it is correct, it is simulated correctly, and if you feel the design you have written is functionally correct, then only we basically go to FPGA because for this small design only it is going to take this much of time, and for larger designs it is also going to take so much of time. So we need to wait for this. And here we can see in the design runs, LUT utilization is happened already, and we are having only one LUT utilization for implementing this. Okay, because for this, okay, we are getting some bitstream error. Let us check what are we getting. Okay, messages. Yeah, this is what I was waiting for. Okay. So we are getting a bitstream error. Now, why is that we are going to get a bitstream error? Because we haven't physically connected this inputs and this outputs. Okay. So we have a board with us. We have a FPGA board with us because we have entered the part number and everything. Now we need to make the physical connections. Like we need to connect this A to some of the input, and we need to connect this B to some of the input, and we need to connect this carry to some of the output, and we need to connect this sum to some of the input. That is, we need to have the constraints over here. Constraints is nothing but you are basically physically assigning the inputs to one of the pins, input buttons or push buttons or switches, and outputs to one of the LEDs or something, right? After that only you are going to generate your bitstream. See, you are going to get an error which is unconstrained logical port 4 out of 4. We have 4 ports, right? Have no user specific location constraints. This may cause I/O contention or incompatibility with the board power or connectivity, affecting the performance signal integrity in the extreme cases. Okay, so this is the error which we are going to get. Problems with the ports A, B, carry, and some, because we haven't connected to the physical thing, right? So this is the thing which we are going to get. Now, tomorrow in next session, we are going to have with us a physical FPGA board with us. I will show you what are the switches, what are the push buttons I'm going to have, and how to make the actual connections. And I'm going to run this particular code on a physical FPGA, so that you will come to know, okay, this is how we are going to make the connections, and this is how we are going to generate the bitstream and run our code on an FPGA. Okay, yes, so that's about this particular session. So the agenda for this particular session was to introduce you with an bit file, what is a bit file, and where you can actually store your bit file, and what where you can store a bit file permanently, so that it is not going to get erased even if you are going to switch off the power. And introduction to your Vivado tool, how you're going to create a project, and how you're going to generate a bit file, and how to create a Verilog file, and those things, right? So that's about this particular session. Thank you. If you have any doubts or any other queries you wanted to discuss, you can